Good evening, or morning or afternoon, whatever time you're watching this. I'm sure this video will be a Hollywood blockbuster, but we are shooting on a low budget here, so be patient in case of glitches. I decided not to use the webcam, so you won't be able to see me. I think it's a lot more important that you be able to see the screen. Let me show you first what software we will be using, and then it's up to you whether you choose to follow along and try to work along with me. First of all, I'm going to go back to page 58, this question of whether we can use body measurements, vertical jump height and wingspan, to predict gender using a neural network, a perceptron. And I want to use both Excel and Maple on that. And then we'll go on to page 61 and start a different topic called the delta rule for neural network approximation. And likewise, be using Maple for that as well. As far as which Maple files, Neural Perceptron 2D, and then Neural Delta 2D. So one of the advantages of a video format like this is you can stop the video and load those files and get that software ready if you do plan to follow along. Okay, let's go back to this problem. We had commented that yes, the neural network does have a chance of learning gender distinguishing, but the scaling on the vertical jump measurements and on the wingspan measurements are far apart, and so the wingspan might overwhelm the vertical jump, and it would be a good idea to do a rescaling to bring these two sets of numbers more in line with each other. And so we had gone through the algebra to find transformations to do that. These were equations for converting a raw vertical jump height to a scaled one, and a raw wingspan x2 to a scaled one. So let me go into Excel first. Let's enter the original data. There are jump heights and wingspans. And down columns. And the genders, I'm going to enter the zeros and ones directly into Maple later, so they could go in the Excel spreadsheet, but there's no need to do that. Then let's build a column of scaled jumps and scaled wingspan. And we developed formulas for those. For jump equals 0.19. That's what I wrote on the worksheet. I'm going to carry a little extra precision if you actually use those formulas. 0.1905 times the original jump height, and then minus 2.8095. And drag this down, and we can see that we have indeed converted the jumps to scaled versions between -1 and +1. For the wingspans, approximately 0.1333 times the original wingspan minus 8.4667. Drag that down. And there again, we've converted the wingspans to something going between -1 and +1, essentially. Okay, I have loaded the add-in, remember, for transferring from Excel to Maple. And so let's take these scaled versions and copy them. And now I'm going into Maple, into Neural Perceptron 2D, and I'm going to try to put that information right here. So I'll copy and paste. And depending on, let me delete this space, depending on what screen you're at when you do the copy paste, you might get different display here. If you want to see how Maple is interpreting what you've copied and pasted, if you replace the colon at the end by a semicolon, then when you push enter, Maple will indeed echo this input. In the meantime, the number of vectors, now why doesn't Maple let me enter something here? The number of vectors is now 6, and for the true outputs, let's call a female a 0 and a male a 1, and so 0, 0, 1, 0, 1, 0. You might wonder why I didn't type this into Excel and then copy and paste that as well. It turns out that Maple wants the t-values as vectors, and for Maple that is something a little different than a matrix, so copy and pasting doesn't seem to work very well for the t-values. Let's also have Maple echo that. Alright, now let's get started. Pushing enter through here. These initial weights and number of trials, alpha, x min max, y min, x2 min max, and so on look pretty good. I'll push enter there and here. And here is my matrix of inputs. Here is my vector of correct answers. Looks like Maple is correctly interpreting what's going on there. Alright, then I shouldn't have to change anything here. I'll just push enter. And let's take a look at what we have here. This is scaled now, remember, so everything is near the origin. But if you look at the data table, there are 4 ladies who are circles here. And then there are 2 males out here. And the situation looks promising. The neural network at the moment doesn't know the difference. The dividing line is not separating circles and squares, circles and boxes. But the 2 data sets do seem to be what's called linearly separable. In other words, I can look at this picture and easily visualize a line where the circles are on one side and boxes are on the other. And so there's a good chance that learning could be successful here. Let's see what happens when we run this. And there is a situation where it is successful. It's actually not what I expected. I would have expected a line more running this direction as I move the arrow back and forth. But you don't have control over what decision boundary Maple actually chooses, or the network actually chooses. Here is one that splits them. So I'm going to jot a note here of the weights. W0 is 0.002, W1 is 0.0501 approximately, and W2 is about negative 0.0140. Alright, and that did seem to be a successful learn. So now come to the worksheet and let's draw what Maple came up with. First of all, there is the network output here, and then 3 things are coming in. There is the 1, and there is x1 prime and x2 prime coming in, and the associated weights then were 0.002, 0.0501, and negative 0.0140. This is Y, the output, where an output of 0 is a woman and an output of 1 is a man. So now the network has been taught. What happens then when you want to use this thing? Because you don't build neural networks just to train them, you build them to later do recognition of people or inputs that the network has not seen before. That's called generalization. So suppose along comes a new person, and we want to know the person's gender, and it would be too boring to just ask them or look at them, and so let's ask them to do a jump for us, and also we'll measure their wingspan. The new person, when I take those measurements, has a jump of 15, say, and a wingspan of 67. Now we want to know whether this person is a guy or a girl. First of all, you'll want to do the scaling. So remember back here, x1 and x2, the original physical variables, are coming into a scaling factor here. That's the equations converting from x1 to x1 prime and x2 to x2 prime. If I use this first equation, I can find that x1 prime is about 0.048, and that x2 prime is about 0.4644. Alright, so how do I now tell whether that's guy or girl? U, remember, is now x prime dot w. These are vectors. Give myself a little more space here. And if I work out what this is, x prime has the artificial 1 in front, and then times, and w0 is 0.002, plus x1 prime is 0.048 times w1 is 0.0501, and plus, and x2 prime is 0.4644, and then times w2, which is negative 0.0140. Okay, now I'm going to punch this into a calculator. 002. Check my work here. And I got negative 0.0021. Remember what that is. That's U, the dot product, and finally Y is f of U. F, remember, is the step function. We're back here. It's 0 if the input is negative, if U is negative, and it's 1 if U is positive. And we got a negative number for U, and therefore the output is a 0, and we say that this person is female. Now notice that U was very close to 0. That means that this was a very close decision, that this person's physical measurements that we took are almost right on the decision boundary. But if this is going to be something that makes a decision, then the call came down that this person is female. You have some homework questions that involve doing things like that. So remember the business about scaling to help make the network work better. And then after you train the network and identify the final weights, if I ask you to classify some new vectors, new inputs that the network has never seen, then you'll have to go through this manual process like this. Or of course you could take these weights and plug them back into Excel and implement the scaling in Excel, which you've already done, and do that if there are multiple new inputs to be processed. The first part of this is called training, when you find the weights of the network based on the inputs you have available at that time, and then you take the model out into, that's building the model, then you take the model out into real life to use it, and here's an example of testing the generalization ability. And that finishes what I have to say about perceptrons for the moment. We may come back to some extensions of that later. For the moment, let's then go on to page 61 and talk about something else. Still using neural networks, but the question now that we want to ask or solve is different. Here are a number of inputs that I would like to learn with a neural network. But this time, instead of the outputs just being zeros and ones, or male and female, or boxes and circles, the desired outputs are real numbers, continuous real numbers. And so, even though there are some similarities on the surface, conceptually this is a little different. Instead of classifying into two categories or even into more than two categories, this is prediction or approximation. I want to train the network so that when it sees the vector -1, 2, it outputs a 0.9. When it sees -2, 0, it outputs a 0.7, and so on. And then I have in mind that I'll come along with a new vector, 1, 1, for example, and okay, what is the appropriate output for a new vector that hasn't been learned? So we'll still use the similar structure here with two inputs feeding through two weights into the summer, and the hardwired one feeding through a weight into the summer or summation device, and there'll still be an f function in here. But now let's switch the output function. It would not do, of course, to have a step function anymore that could only be 0 or 1, because these outputs are not restricted to 0 or 1. So I need a continuous function for my output now. And let's talk about this function listed here. If I draw a graph of y versus u, the function that is commonly used is called a sigmoid function, or a learning curve. It has the structure 1 over the quantity 1 plus e to the negative u. Alright, let's look at some values, and without a graphing calculator we can figure out what this looks like. When u equals 0, e to the u is e to the 0, which is 1, and then I have 1 over 1 plus 1, and that's 1 over a half. So the y-intercept is a half. When u becomes a large positive number, u is a large positive number, then e to the negative u is e to a large negative number. If you think about the graph of e to the x, when the exponent gets large and negative, the exponential basically goes to 0. So in the limit, this term in the denominator is going to 0, and the entire fraction then will go to 1, and that's in the limit, so it's a horizontal asymptote. So out in here, we're asymptotically approaching y equals 1. How about the other direction? As u goes to negative infinity, then e to a large positive number explodes. Think about the graph of y equals e to the x. E to the large positive number explodes, and so the one term in the denominator is getting very, very large, and the whole fraction goes to 0. That's all in the limit again, and so there's a horizontal asymptote on the left of y equals 0. And this is a continuous function. It's built out of a smooth exponential, and so what you see is a shape like this. There's no kink in the graph here. It's a smooth curve changing from concave up to concave down. All right, and so you can see that y now can take on any value between 0 and 1, so there is a shot at being able to learn these values. Okay, let's look at an algorithm to train this neural network. I'll choose a learning rate before, and now here's a new concept that comes up, an error tolerance. I'm going to be trying to learn these values, but these are real numbers, and so it's not really fair to expect the network to get exact answers. I mean, if I got 0.9001, for most purposes that would just be a splendidly accurate answer, or 0.6993, that's a great answer for approximation work like most science and engineering is. And so instead of insisting on exact equality, I insist on equality to within a tolerance. The difference between the teacher answer and the network answer, if it's less than the tolerance, that's okay. Again, just like with the perceptron, we'll initialize the weights to some small random values. We'll go through the set of training vectors. We'll input one vector at a time and compute w dot x. That's u. Feed that now into this new function f, and that gets my network guess. The network outputs a number called y, and that's what it is predicting the output should be. Well, I do have teacher values. I have t values, and so I want to take the y's that the network guesses, compare with the t's that the teacher says are the right answers, and adjust the weights. Let's go to the next page. We'll put the formula here. Let's go to the next page and do a derivation of how this would work. Notice that the error, I'm going to use what's called the sum of the squares of the error. So for each of the vectors, the teacher answer minus the network guess squared, that's the square of the error, and all of those errors, individual errors, are to be added together to be a total error, which I would like to make as small as possible. Let's look at just one input vector, which has teacher answer t and network guess y. I want to adjust the individual weights, and in particular let me talk about a generic one, w sub j. Well, first of all, it's not clear even what adjusting the weight does to the error. So E equals, well, it's t minus y, quantity squared, but y is f of u, and u is w dot x. So yes, changing the weights does change the error. All right, and so if I conceptually think about that for a moment, if I take one of the weights, wj, and plot E versus that, it turns out that what you typically are going to see is a graph that looks like this. Not necessarily a parabola, but something that often comes down to a minimum and then goes back up again. And of course we're looking for this value, the best jth weight, which will help minimize this error. From calculus, we know how to look for minima like this. We should take a derivative and perhaps set it equal to 0, or at least look at where it's positive and negative and think about the first derivative test and decide what might be happening near this point. So okay, let's talk about a derivative. Partial E, partial wj. I'm using partial derivatives because there are multiple weights, a w0, w1, w2. And this is a good exercise with the chain rule. Let's start here, and remember the w's are buried inside y. So if I use the chain rule, here's a 2 times t minus y to the first power, and then the derivative of minus y with respect to wj, I'll write like this. Actually, partial y, partial wj. Now let's keep going. Y is f of u, and so again using the chain rule, and I'm just recopying what's here. Let's take this negative sign out front, and now the derivative of f of u with respect to w. Here's f of u, and I'm differentiating this with respect to w. The w is inside the u, and so another application of the chain rule. This is f prime of u, and then partial u, partial wj. But the w's are still inside u. And if I look at what u is, it's w0 times 1 plus w1 times x1 plus w2 times x2. And I'm thinking about w j being, say, x1 or x2. Could be, let's see, what did I just say? I'm thinking about j being 1 or 2. It could be 0 as well. Let me think about specifically, say, the case right here when j equals 1, and then I'm talking about what's the derivative of u with respect to w1. Well, notice the first term doesn't have a w1 in it, nor does the third term, and so those two terms have derivative 0 when I differentiate with respect to w1. The second term, middle term, does have a w1, and its derivative would be, partial derivative with respect to w1 is x1. So if I copy this, minus 2 times t minus y, f prime of u, and then times x1, or in general, xj. And here then is an expression for the change in error with respect to a weight. So let's write down what a derivative tells us. A derivative tells us how the error changes as wj increases. So So change in y over change in x. As w increases by a certain amount, e will change by this amount. Now, look at what we have. If I'm currently right here, then the derivative is the tangent slope of the tangent line, remember. Here I'm in a situation where to go to the best weight, I actually want to increase the weight. And yet the derivative is negative. Let's go over to the other side. If I'm instead currently at a weight like this, then to move toward a better weight, or to adjust the weight in the proper direction, I want to decrease the weight, and here the derivative is positive. So slope greater than 0, slope less than 0. And in both cases, the change in w has the opposite sign of the slope. If the slope is negative, I actually want to increase w. If the slope is positive, I want to decrease w. So to decrease error, move in the opposite direction of the sign of the derivative, or just say of the derivative. And so what I'm saying in a very long-winded way here is the change in wj should be not negative times something else, but the opposite of that. So negative of a negative, and now the 2 is a constant, the t minus y and so on are constants. I don't necessarily know what those constants are, and I'm not prepared to decide how big of a step. I just know that which direction I need to go. So let's throw in the learning rate alpha there, and then I'll recopy the t minus y, the f prime of u, and the xj. So what I've really done here, again, is drop the negative sign so that I move in the opposite direction of the slope, which is the right thing to do, and replacing the 2 by something probably smaller than that, so that I take a small step rather than a gigantic step. Notice that if I'm here and I take a huge step, I shoot past the proper weight, and then if I took another step back, I might get in a situation where I'd seesaw back and forth and not be able to settle in on the best weight. Okay, so this is how wj changes. There's an xj, and all right, I could have put a w1 and then I have an x1, a w2, I have an x2, or just as a vector. Delta w, delta vector w, is alpha t minus y f prime of u times vector x. And this is the change in weight, so if we come back to our expression, the new weights are going to be the old ones plus that change in weight. So here's the update rule now for the delta algorithm. And so each time the network sees a vector, it'll update the weights according to this rule, and I'll show all the vectors, and then I'll go back and show all the vectors again, and go back and show all the vectors again, and hopefully as I learn, the total error will be coming down and down and down, and I can stop when one of two things happens. Either the total error gets smaller than my tolerance that I set at the beginning, or it's not going down anymore, and I can see that basically the learning was a failure, that the network isn't going to be able to learn this problem that accurately. All right, let's go to Maple again. And this time I want the program called Neural Delta 2D. There are two versions of Neural Delta. One has two-dimensional input and shows graphs, and the other you can have inputs of other dimensions, like 3 vectors of length 3 or 4, 5, and so on, but doesn't show graphs. Okay, here's the version that does show graphs. Up here in the first block, you should never need to change anything there. Here is where you get the opportunity to set the initial randomly chosen weights. 0.1 is usually okay for that. You get the chance to set a maximum number of trials. Again, you don't want to let this thing go forever and get in an infinite loop, so this is telling how many times it should learn before it gives up. Here is the maximum error allowed. This is the epsilon that we were talking about. Here is a learning rate, 0.5 or something maybe smaller than that. Let me change this to 0.05 for the purposes of this example. Here are my 4 vectors for the example I'm demonstrating. Here are the inputs in a matrix, just like for the Perceptron algorithm, and the teacher or correct answers. So I'll push enter through all of this. And the next block of code is going to initialize the weights and then draw an interesting plot. So this is a 3-dimensional plot. Notice that we have scales here of x, which is x1. Maple's language is going to be xyz here, but this is x1, this is x2, and then here is y or t. It's both, actually. Now you'll notice 4 small dots there. Those are the actual points with their x1, x2, and t. These are the points that we're trying to learn. And then the network is using the randomly chosen weights and computing, this time not a decision boundary, but an output surface. So it's saying that if I have a value of x1, x2 here, and then I plug that into my network, that the y value is right in here, wherever directly above that x1, x2 point. When I go up and hit the surface, that's the network's prediction for that input. And different inputs, different x1, x2, you see, are resulting in different y's or different outputs. Right now, the output surface looks approximately like a plane. It actually isn't exactly, because the f function is not linear. And it's not doing too well. The plane, the y values, are not close to the dots whose heights are the t values. So there is learning to be done. And let's see if this network can do something about that. So when I push enter, a lot is going to happen here. I'll just stop for a moment and let it run. Then we'll go back and look and see what happened. So the fan is coming on my computer. There's a lot of computation going on here. Remember, it's going to stop when one of two things happens. Either I hit 20 iterations, or my error has gotten below the tolerance that I gave. Okay, let's go back and remind ourselves of what we put in. The maximum error was 0.01. The epsilon was 0.01. And as far as what the network is doing, scroll up to see like the first iteration. So there was the original graph, and now here it is. Here's the original graph. Here it is trying to learn now. So it's saying, okay, I'm trying to learn vector number 1. Here are all of the teacher answers, the correct answers. Here are what the network is guessing. And in particular, for vector number 1, the teacher answer is 0.9, whereas the network is guessing 0.46. That's not close at all. This is the E total. The algorithm Maple is computing this. So there is learning to be done. The network does so. Here are the new weights, and you'll notice the error was 0.6877, and now it's gone to 0.6831. So that's not much of a change, but it is a change, and it's in the correct direction. It's getting smaller. And so then we show vector number 2 to the network. The correct answer is 0.7. The network is saying 0.49. There is some learning to be done. The network changes the weights, and the error drops from 0.683 to 0.678. Again, small change, but in the right direction. And you'll notice that if you scroll through these slowly, the error total is going down slowly but surely. So let's jump ahead. And down here in the middle somewhere, the error is down to 0.46. And if I take it some more, the error is down to 0.37 or so. And by the time it finally timed out, the error is down to 0.366. And undoubtedly it timed out because of my 20 iteration limit. The error is not within the tolerance, but I told it to stop after 20 iterations. But what you may notice is that before we had a plane, the output surface was a plane, and it wasn't particularly close. This learning has now caused this thing to warp a little bit. It's not flat anymore, and in particular it's bent down so that this end is near the dots. I'm trying to get this thing rotated. It's bent down so this thing is much nearer these two dots, and this part is up here nearer these two dots. And so some learning has taken place. I still have some error, and especially with this point, I'm not very close to this point. So I might want to let the network run longer. The program Neural Delta does the same thing, only it's not going to print the graphs, and that's what's taking the time. So if I come back up here, and same inputs and everything, except I'm going to change the maximum number of trials, say, to 200 instead of 20. And let's see what can happen here. So here are my initial weights, and let's let it run. And this is going a lot faster because of the no need to print graphs. And what we saw was the error was dropping down fairly rapidly at first, and now it's still going down. You can read this rapidly flashing screen perhaps, but it's not going down as fast. We should be timing out here before too long. At least I hope. By the way, if you ever need to break Maple out of a computation, up here this stop sign symbol with a hand in it, if I click that, it breaks out of the computation. I'll let it run here for a little longer. This is 200 loops, and there are 4 vectors. So we're running a vector through 800 times total, and we've managed to get the error down to 0.093, which is pretty decent. Let's go back and look at the final output here. The teacher answers are here 0.9, 0.7, 0.2, 0.1, and the network is saying 0.84, 0.74, 0.24, and 0.05. So that's not great. I'm still not within my 0.01 error tolerance, but it's much better than I initially started out with for my randomly chosen weights. A lot of learning has definitely taken place. All right. And so that's the delta rule. We may do some more with that next class. And let me skip the example on page 65 for now. We may come back to that or to a similar example next time. And let me finish quickly here with page 66. So what are some things that you could carry on from here? This is an interesting apparatus here, a neural network that's able to learn, but it doesn't seem particularly useful because the problems that we're looking at, the applications we're looking at, are so limited, so small. There'd probably be much better ways to solve all of the problems that we looked at. Let's tweak things, at least look at the concept of how you would tweak things a bit here. And let's go back to classification. The boxes and squares, or in this case, I'm saying I want to separate points by color, where I have this time reds, yellows, and blues. And I want to draw a decision boundary here to separate the different colors. And you see, well, clearly one decision boundary to split into two halves is not enough. There are three categories. So what could we do about that? Well, I can draw two decision boundaries if I want. For example, if I put one decision boundary right about here, let me redraw that. I'm going to hit point. If I put one decision boundary right here and another decision boundary right here, and if this is number 1 and this is number 2, then if I know which side of number 1 I'm on and which side of number 2 I'm on, I'll be able to tell you whether I'm in red land or yellow land or blue land. So how could a network do this? Well, one perceptron couldn't, but what if I have more than one perceptron? So two perceptrons, they each have their output, y1 here and y2 here. And then I have inputs, x1 and x2, and each perceptron is going to get each input. And I'm not going to draw the weights here, but there will be a weight on each of these 4 links plus the hardwired one coming in. And then as far as how to interpret the output, if I look at this, here is boundary number 2. Let's suppose that this is the 0 side and the 1 side. I'm imagining that I've already trained the network and it's formed these two decision boundaries. Perceptron number 1 is forming this boundary. Perceptron number 2 is performing this boundary. Suppose number 2 has split like this. Well then, if I look at this, what I'm saying is that if the output number 2 is a 0, I have a red. So if I come here and if this is y1, y2, then this is a red. Its output number 2 is a 0, and this is a red. If output number 2 is a 1, then I want to look at output number 1, and suppose for the sake of illustration that number 1 has a 0 side and a 1 side like this. So if number 2 is outputting a 1 and number 1 is outputting a 0, I'm over here in yellow land. If number 2 is outputting a 1 and number 1 is also outputting a 1, then I'm in blue land. So I'll train the network, and then when I want to use it, I put in my 2 inputs, which are the coordinates of a new point. So along comes somebody new, and if he happens to land out in here, the network is going to pick up that he is in red land, even though he doesn't look like it. So by adding more and more perceptrons here, I can code higher and higher numbers of categories. 2 outputs could code as many as 2 squared or 4. If I have 3 outputs, 2 cubed is 8 different categories that could potentially be learned, and so on. So that's one type of generalization that we might want to look at. And another is, what if I have a situation where the vectors are not linearly separable? If I'm trying to separate the boxes from the circles here, there's just no way that a straight line is going to do it. But if only I could train a network to learn a curved boundary like this, then the 2 sides of this boundary definitely do separate these types. And so how would you do something like that? Well, you need more neurons again. And this time, perhaps, you might want to arrange it like this. So here's an output of 1. And now here are 2 neurons whose outputs are going to be inputs to the next neuron over here. And then I have inputs x1 and x2, and each of these is going to get fed into the others. So x1 and x2 get fed into what are called the hidden neurons, and then there's an output neuron which produces the final output. And it turns out that if you have a structure like this, that yes, the boundary surface decision boundary is not necessarily linear anymore. It can be curved, and therefore you can learn more complicated problems. So bottom line for both of these, if you have a bigger problem, then you need a more powerful brain. You need more neurons. All right, I think that finishes what I have today. So we'll pick up again on Monday with this.